In the late 19th century, physicist Max Planck was trying to mathematically model blackbody emission of light. Previous attempts had failed to describe the behavior of blackbody radiation over the entire spectrum. It had been assumed that the energies of atoms behaved much like energies associated with other familiar systems. Planck's breakthrough came when he restricted those energies to discrete values. Atoms of the same element would have the same allowed energies, but those values would differ from the allowed energies of other elements. Atoms then had to gain or lose energy by the absorption or emission of packets of energy. Einstein would show that these packets were actually individual photons. Some additional terms are needed for further discussion. For simplicity, let's restrict this discussion to the hydrogen atom. A hydrogen atom has only one electron. The energy of an atom is basically dictated by the location of its electron. When the electron is in the lowest state possible, that is, when the atom is in the lowest state possible, the atom is in what is referred to as the ground state. When in the ground state, electrons tend to be closer to the nucleus. The nucleus is positively charged and electrons are negatively charged. The closer opposite charges are, the greater the electrical attraction and the more tightly bound the electrons are to the nucleus. If electrons have more energy than the ground state, the atom is in an excited state. If an electron breaks free, then the atom has been ionized. Shown here are the allowed energy levels of a hydrogen atom. The unit of energy used when dealing with atoms is the electron volt. The energies are negative, indicating that the electron is bound to the atom. The lower the energy, the more tightly bound the electron is to the nucleus. The ground state is minus 13.6 electron volts. At energy of 0 or greater, the electron breaks free and the atom is ionized. Electrons jump instantaneously from one level to another by the emission or absorption of one photon per jump. They can only go from one allowed energy level to another allowed level. Thus, only certain photon energy will be absorbed or emitted. The photon energy will be equal to the energy difference between levels. Photon energies are always positive, so don't get too hung up on the sign. The sign just indicates whether a photon is emitted or absorbed. When an electron absorbs a photon, it goes up to a higher energy level, indicated by the upward arrow. The electron will spontaneously drop back down in energy by the emission of a photon, indicated by the downward arrow. The energy difference between the ground state and the first excited state is 10.2 electron volts. An electron can jump from the ground state to the first excited state only by the absorption of a photon that possesses 10.2 electron volts of energy. If an electron in the ground state absorbs 13.6 electron volts or more, the electron breaks free from the nucleus and the atom is left ionized. Since electrons will only emit and absorb photons with certain energies, and since the energy of a photon is precisely related to its wavelength, then only certain colors of the spectrum are emitted or absorbed by a gas of hydrogen atoms. Energy levels are labeled here by an index n. Suppose one has a gas of excited hydrogen atoms. When electrons in those atoms make a transition from n equals 3 to n equals 2, that corresponds to the wavelength of the red light. If you look at the spectrum, this would be the red line on the right. This is an example of an emission line. A spectrum of emission lines is an emission spectrum. Different energy level transitions result in different color emission lines. Only a few energy level transitions emit photons that are within the visible domain. Most of the transitions emit photons that are outside the visible domain. Under certain conditions, one can have absorption spectra, as shown below the emission spectrum. They appear as continuous spectra with dark bands that correspond to colors of light that have been absorbed. These dark bands are called absorption lines. It is important to note that the wavelengths of the absorption lines are the same as the wavelengths of the emission lines in the emission spectrum. Collectively, absorption and emission spectra are called line spectra. Since each element has its own unique set of allowed energy levels, they each have their own unique line spectra. Some sample emission spectra are shown. Line spectra are like the fingerprints to the elements. For example, By collecting light from a star, creating a spectrum and analyzing the absorption lines present, one can determine what elements are present in that star. Shown here is a power spectrum. In power spectra, vertical spikes are emission lines. Analysis of line spectra is not limited to the visible domain. These are emission lines that are actually at wavelengths corresponding to X-rays. These are very energetic photons coming from near neutron star. Computers have been used to identify the elements in the environment of the neutron star. Those atoms are being very energetically excited, and when they de-excite, they emit high-energy photons. When an atom is bound up as part of a molecule, this adds additional allowed energy levels due to additional rotational and vibrational energies. Even if the atoms are of the same kind, the line spectra become more complex. Each compound also has its own unique set of allowed energy levels. Thus, by analyzing spectra, we can also determine what compounds are present. Absorption lines occur when photons from a continuous light source, like the surface of a star, passes through a cooler gas cloud. Photons of certain wavelengths get absorbed and re-radiated. However, when these photons are re-radiated, they usually do so in different directions. This leaves the dark absorption lines in the spectrum. On the top left is an absorption spectrum and its corresponding power spectrum just to the right. It's basically a black body curve with absorption lines appearing as downward spikes. On the bottom left are emission lines and its corresponding power spectrum. The emission lines appear as upward spikes. You should be able to identify a spectrum as either an emission or absorption spectrum.